Hi guys, so here we have a question about two capacitors in particular. They're connected to a battery in parallel. So this is what the circuit would look like initially. They're connected to a 35-volt battery in parallel. And we know the capacitances of each of those capacitors. And then we're told that the battery is going to be removed and the plates of opposite sign are connected. And we're supposed to find the final charge and potential difference for each capacitor. I'll start with something simple. Initially, we have this circuit, right? We just connected the battery. Let's say that we just connected the battery. Current is going to flow in this direction until each of these capacitors become fully charged. And what's going to happen then is we're going to have a fully charged capacitor here and a fully charged capacitor here. And then when we remove the battery and connect plates of opposite signs, what we're going to do is flip one of the capacitors, flip it upside down. So that's what we mean by connecting plates of opposite sign. This positive plate of this capacitor will connect to this negative plate of this capacitor. And of course we'll do the same thing kind of like down there. So now that that is out of the way, initially we know that these guys are in parallel, and when capacitors are in parallel they both have the same voltage. The voltage of each of the capacitors is 35 volts. Think of it like resistors. When they're in parallel and they're connected to a battery, both of the resistors would have the same voltage in that case. Now what I'll do is, in this initial circuit, I'll first work on finding the equivalent charge, or the total charge, from each of these capacitors. The idea in general would be that in these types of questions is that if you have capacitors that are in series, they would have charges that are equal to each other. But in this case they're in parallel, so the charges aren't equal to each other. But of course the voltages are. So what I'll be doing is I'll solve for the equivalent capacitance first. These guys are in parallel. Now for capacitors, we use the parallel rule to add up the individual capacitances. And the parallel rule for capacitors would be like the series rule for resistors, where we add up the resistances directly without taking their inverse. So in the case of capacitors, when they're in parallel, you add them directly, each of the capacitances. So it's kind of like the reverse of resistors, the reverse of how those rules apply for resistors. So we know that the capacitance of one of these capacitors is 3 microfarads. For the other one, it is 9 microfarads. So that's an easy calculation. We get 12 microfarads. Now I can find the total equivalent charge, which is going to be 12 microfarads multiplied with 35 volts. Which is going to be equivalent to, I'm just going to get my calculator. So 12 microfarads times 35 volts, that gives me 420 microcoulombs. Coulombs of charge. So that means that Q1 plus Q2 equal 420 microcoulombs. Now I'll find the individual charges on each of these capacitors, because now I can do that. And we're still looking at the initial state. We're not going to focus on the final state just yet. The one thing I can keep in mind though for now is that regardless of whether I'm in the initial or final state, the net charge will always be 420 microcoulombs. The charges can't be erased. Charges are conserved, so you can't get rid of them. It's kind of like saying there's a better analogy to use here, which is I guess to say that, for example, that energy is conserved. You can't get rid of energy. It has to be conserved. So whatever the energy is initially will equal to the final energy as well. The initial and the final energy are always equivalent to each other, maybe in different forms. That's what we learned in mechanics. So the same thing with charge. It's conserved. It doesn't change, the net charge at least. Of course, the charges on each of the capacitors will change. Now I can find the charge on the first capacitor. Q1 is equal to C1 V1, and then I can find the charge in the second capacitor, which is equal to C2 V2. C1 is 3 microfarads times 35 volts, and I'm gonna have to start erasing some work, so I'll get rid of the equivalent capacitance. I'll move this, I'll move this down here, and I'll do that after again. So 3 times 35 volts is 105 microcoulombs. So that's the charge on the first capacitor initially. Now for Q2, we have 9 microfarads times 35 volts, and that's going to be equal to 44. Sorry, give me a second. I have to multiply here. I knew something was off. 315 microcoulomb.